Here's kind of a fun related rate problem. Suppose now we have a big cube of ice and it starts to melt in such a way that each of its edges decreases in length at the rate of 2 centimeters per minute. Now, at what rate is the cube's volume changing when each edge is 100 centimeters long? So let's start by drawing a picture. So we'll draw a cube as best we can. I'll draw a square and I'll make it look 3D. All right, so here's a cube, and since it's a cube, I'm going to label each of its edges the same length, x, x, and x. Maybe I'll put that x over here. Now I'm going to write down what I have and what I want to find. So what I want to find is this. Down here at the bottom it says, at what rate is the cube's volume changing? All right, so here's what I want. I want to find, now it's a volume. So dV now is respect to time, right? Because as the ice melts, look what I have. Here's how I know it's a dt. Look down here. 2 centimeters per minute. So the bottom number is a minute. That's the time. So I know that everything here is with respect to time. So find dV dt when, well, what do we know? We know that the edge, right over here at the left, the edge is decreasing in length at the rate of 2 centimeters per minute. So these edges, each edge is shrinking. It probably comes in from both sides, but it's shrinking at 2 centimeters per minute, right? So this is coming in this way. I'll try to draw that a little bit here. It's coming in this way. Maybe this is coming in this way, and this is coming in this way. So when, here's what we know, dx dt equals, now it's coming in, it's shrinking, so it's negative 2 centimeters per minute, and I want to find it when x is equal to 100 centimeters, right? That is right down here at the end. So I need an equation here. So I'm looking for the volume, right? Here's what I want to find. I would eventually like to get a volume equation, and it turns out I can't do this directly because it's a cube, and here's what I know. I know that the volume of a cube is equal to, now it's the length times the width times the height, which in this case is volume is equal to x times x times x, or the volume is x cubed. Now let's differentiate each side with respect to t. Now, I'm going to do this again. I'm going to do this very carefully, so I'm going to write everything as a function of t. So this is equal to the volume, right? The volume changes, the volume depends on time, and this x value, the length of the edge, well, that depends on time too, on time also. So this is going to be x of t cubed. Now when we differentiate, I'm going to get dv dt equals, now over here, this is a power, right? I've got this base to a power. I'm going to bring the 3 down as a multiplier and decrease it by 1. So we'll get 3 x of t squared. That's the derivative of the outside, right? Chain rule, power rule. Derivative of the outside times, now the derivative of the inside, well, I'm just going to write dx dt, right? Just differentiate this with respect to t. So I'll indicate that because I don't know exactly what that function is. All right, so this is derivative of the outside times the derivative of the inside. Now this is really just this. dv, let's see if I can actually write that so it looks readable. dv dt is equal to 3x squared dx dt. All right, now up here, let's substitute. I'll substitute 100 for 100 centimeters for x. Don't forget the units. And then dx dt, we're given that to be negative 2. Negative because it's decreasing in size, right? It's melting. The ice is melting, so it's getting smaller. Negative 2 centimeters per second. So let's substitute. So we will get that dv dt equals 3 times 100, let me get those units in, 100 centimeters, I better write it like this, 100 centimeters squared times -2 centimeters per minute. So let's multiply. We'll get dV dt equals 3 times, now 100 squared is 100 and then 2 more zeros, right? So that'll give us 10,000. Now this is why I like to write the units. I'll get the 100 squared and then also centimeters squared. So centimeters squared times -2 centimeters per minute. So let's make that multiplication now. So we'll get dV dt is equal to, all right, let's just multiply all through here. Here's what we have. 3 times 10,000, 30,000 times -2, -60,000, -60,000. Now what about the units? We've got square centimeters times centimeters. That's going to be cubic centimeters. And it's per minute. Now, do you see that negative? Don't forget that negative. I've got 3 times 10,000 times the -2. That's going to give us that -60,000. So I've got my answer here, but let's write it in a more convenient form and then we'll interpret it. I'm going to say that dV dt is equal to -60,000 cubic centimeters per minute. Now, I'm even going to write this like this. dV dt, I'm doing this so I can make an interpretation. I'll get -60,000 cubic centimeters per 1 minute. Now here I've written the interpretation. Here's how I see this. What I see is this, that when each edge of the ice cube is 100 centimeters long, that means at that particular instant in time, we can expect the volume of the cube to decrease because of that negative. We can expect the volume of the cube to decrease by about 60,000 cubic centimeters in the next 1 minute. So in terms of a picture, here's how you might visualize it. At the time when the ice cube has an edge length of 100, 100, and 100, each edge is 100 centimeters long, in the next minute, right, as the next minute goes by, that cube, ice will have melted and the cube will have shrunk to this cube here. So we're saying that the volume of this cube here is 60,000 cubic centimeters smaller than the volume of this cube.